I'm Keith Sanders, and I'm the General Manager of Skills at Sanders. And this morning I want to talk about pump selection and the basics of good pump selection. The most important factor in making a good pump selection is actually knowing the conditions of service that the pump needs to cope with. Once you've got that information from your customer, you need to match the pump selection to those operating conditions based on the speed of rotation that the client might nominate, and also trying to make the duty point as close to BEP of the pump curve as you can. And then you need to understand how the control system is going to operate on that pump so that it will optimize power consumption in both the operating situation and normal under and overload conditions that the system might produce. So those are the steps that you need to go through before you can actually make pump selections. It's primarily a user responsibility to tell you the conditions of service. The pump people can't know that unless you tell them. So you need to know what is the type of fluid to be pumped, the system head conditions, the flow rate required, is it constant, is it variable, and is there a load profile that tells you what the underperformance and overperformance conditions are, as well as the normal operating conditions. So all this information can only come from the user because he's going to use that pump in those operating conditions. Here's a typical load profile, and you can see that we operate at 80% of flow rate for just under 60% of the time, 60% of flow rate for about 25% of the time, and 40% of the flow rate at about 15% of the time. So that's the way that pump is actually going to be loaded in operation. So you can either control that by varying the speed of the pump or the time that it operates at a fixed speed. That's the way you deal with those sorts of situations. But pumps seldom run 100% of full load for 100% of the time. That's not the way pumps are normally operated. There are two components of the system resistance that we need to know about. The first one is static head, and that exists at zero flow. And that's just the difference between the surface level on the suction side and the surface level on the discharge side. And you can measure that, or you can calculate it. The second component is the friction losses in pipes, valves, and other pieces of equipment that might be in the flow circuit. That could be a chiller, it could be a heat exchanger, and so on. And then we can plot that information on what we call a system curve. And that system curve is on the same axis as the pump curve. In other words, it plots head against flow. When you're calculating a system curve, you should really use the most up-to-date system data that you have for that specific job that you're making the pump selection for. Not what was done 20 years ago, but what is likely to be installed on site. Okay? So you've got to have the most up-to-date data on the proposed system layout. You need careful selection of the pipe sizes and the pipe materials to give you the minimum friction loss, because friction loss equals power consumption. The more losses you've got in friction, the higher your power consumption will be. And you need to avoid adding contingencies or better fudge factors. I don't know, so I will guess. That's not the way we should approach pump selection, particularly not at the time you're actually going to select the pump and manufacture it or customize it to meet the duty. If we look at systems, there are two basic types. There's an open loop system where the suction pickup point is different from the discharge point. And in such a system, we've got both static head and we've got friction losses. The other type of system we can come across is a closed loop system, and that's where there is no suction reservoir or discharge reservoir. It's a continuous circulation, and that you often find in HVAC systems. In such a situation, the losses in that system are all friction losses. There is no static in a closed loop system. So here we've got a duty that we're given, and this is our duty point. So that's the pump curve. And what I'm trying to illustrate here is that different systems give rise to different operations, not so much for the duty point, but for off-duty conditions. This line here is showing you a system with relatively large pipes, but with a high static head. This system here is showing a recirculating system, so there is no static. And this is one in between, which you might call the normal condition for most pumping applications, where you've got a certain amount of static because it's an open loop system, and you've got a certain amount of friction loss. And where this becomes important is what happens when we move away from the best efficiency point and come back along the curve. We will see that can give rise to unpleasant operating conditions in the pump because we haven't chosen the pump that's closest to its best efficiency point. And we'll go through that a little bit later in this presentation. So closed loop systems are often found in HVAC installations, and the pipe friction is directly proportional to V squared, the velocity through the pipework. And the system curve, usually in the friction component, is a square law curve. So when we're looking at suction pipework, we have to make sure that the suction pipework is at least as large as the suction flange. Suction pipework should be as straight as possible to avoid tees and bends. The pipe suction should be continuously rising towards the pump flange, and we should check that suction pipework is aligned to the pump flanges, not the other way around, and is correctly supported. The discharge pipework, we would normally look for flow velocities between 1 and 3 meters a second. The discharge pipework, again, should be as straight as possible. We check the discharge pipework is aligned to the pump flanges, and we select valves and fittings that minimize friction loss, because friction loss equals power consumption. And finally, gate valves are often used in pump installations. These should not be used to control flow. They are there for isolation purposes only. And you should consider non-return valves to avoid backflow in the system. If we look at the pump and system intersection point, here is your pump curve again, the blue line. Here is your system curve. Here is your BHP curve. And here is your efficiency curve. So that would be the characteristic for a pump that is operating in the red line system. You should understand that a centrifugal pump will always operate where the pump curve intersects the system curve on site, not one you've calculated back in the design office. Okay? So the pump will develop only enough head to overcome the system resistance that it sees in actual operating conditions. So accurate determination of the operating point is critical if you're going to get the pump selection close to the best efficiency point. Here I've got a pump curve which is showing a preferred operating zone, but this manufacturer has given an idea of where to choose the pump operating point if this pump is going to be the basis of your selection. Okay? And that's important because the guy who's making the pump should know where it operates best. In selecting pumps, you are reminded the normal operating point should be as close to BEP as possible. So somewhere in that zone would be ideal. Most pumps curves do not show this information, but you should know that that information is important. And as a rough guide, if it's not shown on the curve, no more than 10% to the right of BEP and no more than 25% to the left of BEP. That's a rough guide of the preferred operating zone.